Okay, so if you remember yesterday, we discussed how to set up this integral. So let's just remind ourselves where we were. We were finding the value of the triple integral over the region E of the function z dv. Okay, so where E was the region bounded by the plane, and then these three planes also. We showed why we ended up with this tetrahedron. Okay, so we need our limits of integration. Now, for your limits of integration, you need to sort of decide what direction you're going to integrate first. Okay, I look at this plane we have here, x plus y plus z equals 1, and there's nothing about it that makes me think I should integrate in a particular direction first. And the reason I say that is because it doesn't say like y equals or z equals or anything like that. And then no matter what variable I pick, like so for example, if I decide to do dz first in this triple integral, z, you can see in the picture, is varying from the xy plane. And what's nice about being in the xy plane is that z is just always 0. Okay, there's that plane right there, actually. And then it varies between there and this tipped over plane, x plus y plus z equals 1. So all my z values vary from 0 up to the surface of this plane. So that's why, and that would be the same no matter what I did. So all I need to do now is say that z varies from 0, and I need to rewrite this as z equals. Well, I can do that quickly by saying z equals 1 minus x minus y. So that's what goes on here. That's how we got that upper limit of integration. All right, and here's the trickier part for triple integrals, usually. For the next set, after we've done dz and taken care of that, you're left with two variables. So here's my advice for getting these correct. Draw that plane, whatever this is. So if it's dy dx, you draw the xy plane. If it had been dz dx, you draw the xz plane, whatever it may be. And then you should think about the shadow of the three-dimensional region. Think about the shadow that this tetrahedron makes into the xy plane. That's what you should think about. Why the xy plane? Because those are the two variables I have to integrate with respect to. So here you are. I am integrating into that shadow. All right? Since dy comes first, we draw a vertical line in the y direction. And we ask ourselves what y varies from and to. Well, if you notice, all the y values, the lowest y values, no matter where I draw this vertical line, are always 0. So that's why there's a 0 on the bottom here. And then y's height depends on what this line is. But you can get the equation of that line using basic algebra from like an Algebra 1 course or something. Here you are. You've got a line whose y-intercept is 1, so it's y equals 1. And its slope is negative 1, so it's going to be minus x. So that's where this limit of integration comes from. Okay? And then lastly, x varies from 0 to 1. So this last set of limits here are just constants. All right? Let's actually compute this integral. You should think of this like nested integrals. So this integral here is the one we've got to compute first. All right? So that antiderivative with respect to z of z is just 1/2 z squared, evaluated from 0 to 1 minus x minus y. Okay? Now, this where someone might make an argument in this problem that this is not the most convenient way to integrate. We'll talk about why in a second. Just take a look at this now. So I have to plug the upper bound in. So it's 1/2 of 1 minus x minus y squared minus 1/2 of 0 squared. Okay. So this is where you might say, this isn't necessarily the nicest thing to integrate with respect to, because some of you may be tempted to square this out first and then try and work things out and so forth. I don't know. You'll have to decide. It's easy to see that if I had integrated with respect to y first, the antiderivative of z with respect to y would just be zy. So it would be a pretty easy expression to look at. Okay? The antiderivative of z with respect to x would have been zx, so that would have been pretty easy to look at too. Anyway, I think I'll just stick with this. Okay? And the next antiderivative is going to be from 0 to 1 minus x dy of this expression. Okay. So what you'll notice is I think we're integrating anti-differentiating respect to y, we could think of this like a chain rule in reverse. We know that the original antiderivative had to have this in it. Okay, so let's think about why that's true. Let's do a little check right now. Let's pretend we're saying, oh, I think that's the antiderivative. Fine, let's check it. So the derivative of this expression with respect to y would be 3 times 1 minus x minus y squared times, because of chain rule, the derivative of the inside. Well, if y is the variable, the derivative of the 1 is 0, the derivative of the negative x is 0, and the derivative of negative y is negative 1. So what you can see now is that if we suspected this was the antiderivative, we're not quite correct, because this thing simplifies to negative 3 times 1 minus x minus y squared. Okay? So take a look at this and compare it to what's up here. Right? So we know that when we take the derivative of this expression here, when we took the derivative, this negative 3 pops out, right? Because of chain rule. And that's coming from here. But the real coefficient I wanted to have here was a 1/2. So there must have been some number in front of this that when I multiply it by negative 3, I would get positive 1/2. So that number must have been a negative 1/6. So let's put a negative 1/6 here and try it again. Now let's check this again and see if this works out the way we want. So check. Here we go. The derivative of this expression. Well, you've got negative 1/6 times 3, because the 3 comes down in front. 1 minus x minus y to the second. And then from chain rule, we get a derivative of negative 1 from the inside. Well, isn't that nice? Because now, look what you end up with. You end up with 1/2 times 1 minus x minus y squared. Okay? Which is exactly what I wanted this to give me. I wanted it to be that. So now I know that this expression here is the antiderivative of that thing with respect to y. Okay? So let's actually write that out. So we're doing the antiderivative from 0 to 1 minus x of 1/2 1 minus x minus y squared dy. That turned out to equal negative 1/6 1 minus x minus y cubed. Okay? We need to evaluate this from 0 to 1 minus x. So let's continue. Here. So now we're going to plug this in for y. So I'm going to get negative 1/6 of 1 minus x minus 1 minus x quantity cubed. Okay? And then I'm going to plug in 0. So it actually becomes minus 1/6 or plus, minus negative 1/6 plus 1/6 of 1 minus x. It would have been minus 0. So then it's really just this expression. Okay, so let's simplify a little bit here. So I get negative 1/6. And then here, well, isn't that nice? That's just 0 cubed. Oh, wow. That's really nice. Plus 1/6 of 1 minus x cubed. So this is all we get. All right, now we're ready for our last integral. From 0 to 1, I'll put the 1/6 down in front. 1 minus x cubed dx. So let's finish off. We need something whose derivative is going to be 1 minus x cubed. Well, it must have had a 1 minus x to the 4th in it, right? Let's do a little check now. If we thought that was the antiderivative, we would check it by taking the derivative, which would be 4 times 1 minus x cubed times negative 1. Or we'd have negative 4, 1 minus x cubed. Well, you'll notice that the coefficient up here is just a 1. So something must have been around that canceled that negative 4 when it appeared. And it must have been a negative 1/4. Okay? So that's the reasoning. Let's check it again and make sure. If we have negative 1/4 of 1 minus x to the 4th, the derivative would be negative 1, 1 minus x to the 3rd, times a negative 1. But that would give me this. So that's perfect. So now we know our antiderivative is this expression. So it's going to be negative 1/4 of 1 minus x to the 4th evaluated from 0 to 1. Okay. Oh, yeah, there's a 1/6. I knew something was missing. I'm like, wait a minute, I'm not expecting this answer. Don't forget that 1/6 from up here. There it is. That guy comes down. All right. So this is negative 1/24 times 1 minus 1 to the 4th. Then minus negative or plus 1/24 times 1 minus 0 to the 4th. So when everything's said and done, you just get an answer of 1/24. Okay. So a lot of work for a pretty small, simple answer. Something fun to think about now is what this answer might mean. Well, let's think about what we were really doing. We were finding the value of the triple integral over the region which was represented by this tetrahedron. So this is 1, 0, 0, 0, 1, 0, and 0, 0, 1. Now, if we're going to think of triple integrals, and they sort of remind us of volume a little bit, there's something strange about this answer. Because without doing any calculus, I know how to find the volume of that shape. It's a pyramid, and volumes of pyramid are always 1/3 the area of the base. I need to be careful here. That's area of the base times the height. Well, in our case, that would be 1/3 the area of the base. That's a triangle. That's 1 by 1. So it's going to be 1/2 of 1 times 1 times the height, which is also 1. So we get an answer of 1/6. So the volume of this thing was bigger than the value of this triple integral. And that's sort of an interesting question. Like, well, why did that happen, right? Well, this integral, this triple integral, what it did was, for every cube partition inside of this solid, it evaluated what the z-coordinate was inside that little box, right? So every one of these little boxes in here, these infinitely many tiny boxes that are inside this tetrahedron, got weighted by their z-value. But if you think about all those z-values, all the z-values in this tetrahedron are between 0 and 1. So you're multiplying by decimals. So none of these little cubes got to contribute a full volume. They didn't contribute a full volume. They contributed some fraction of their volume because they were multiplied by the z-value associated with that cube. And then were all added together. So that's why it makes sense that this answer be smaller. Okay? All right. All right. So let's take a look at this one, because this one has nasty limits of integration. We're just going to start it off and see what happens. Now, this, as scary as it looks, is actually the first antiderivative is pretty easy because that thing has no y in it. So with respect to y, it's just a constant, right, Jerry? Yep. So the antiderivative is x squared plus z squared times y, evaluated from 0 to x squared plus z squared. Okay? All right. So let's take let's plug things in. If I plug in this top expression, I'll get x squared plus z squared times the square root of x squared plus z squared. And if I plug in 0 times this will just go away. So this is the value of the inner antiderivative. Now, if you want, you could rewrite this as like x squared plus z squared to the 3/2 power. Okay, but we're going to run into trouble in a minute. Let's look at this next set of limits of integration. Okay, and I think it's -2 to 2. Yep. Okay. All right. So now, here's where things run into trouble. Yeah, sorry, made a mistake here. This is dz dx. Okay. I think that's okay. All right. So if you were going to attempt to take the antiderivative of this inner expression, you'd run into trouble right away. The problem is that I can look at that and know that it's not the result of a chain rule. The reason it's not the result of a chain rule, because if I were taking the derivative of some expression with respect to z, and got this, right? Let's say for a minute you hypothesized. You said, I think the original expression must have been something like this to the 5/2. You added 1 to the exponent. You said, this must be the original. When you take the derivative of this and you check it, here's your 5/2 x squared plus z squared to the 3/2 times, from the chain rule, to z. Well, there's no multiple of z anywhere present up here. So this could not have come from a chain rule. So we're in trouble. We don't know how to take the antiderivative of this. It's very difficult. But maybe if we re-express it in a new coordinate system, things will be nicer. And it turns out that's true. So watch what happens here. You need to draw the xz plane and think about the shadow or whatever region's being described here. There's a region being described by these things. Well, if z equals this expression to this expression, those are two semicircles. It's an upper semicircle and a lower semicircle. So here it is, from -2 to 2. All right. So circles make me think of polar coordinates. Very easy to describe this region in polar coordinates. Let's think about that for a minute. Our radius, r, is always between 2 and 0, while our angle theta is always between 2 pi and 0. That's a mistake. Our angle theta is between 0 and 2 pi. So that's a really nice way to describe the region. Certainly nicer limits of integration than what we have in this double integral the way it is. Okay? All right. So also, if we're in the xz plane and I want to get r, well, actually, that's not so bad. I can do a little Pythagorean theorem. If this is x and this is z, I know that x squared plus z squared equals r squared. So I'm ready to rewrite this integral. It's going to be a double integral. I'm going to do d theta first, dr second. So from 0 to 2 pi, from 0 to 2, and based on this fact right here, I can rewrite this to be r squared to the 3/2. And then don't forget, you need a correction factor when you convert the polar coordinates of r. So this actually turns out to be really nice, because now your antiderivative, or your double integral, I should say, has turned into r cubed times r to the 4th, d theta dr. Well, this is going to happen very quickly. The antiderivative of r to the 4th with respect to theta is r to the 4th theta from 0 to 2 pi, or just 2 pi r to the 4th. And the antiderivative of that from 0 to 2, dr, is going to be 2/5 pi r to the 5th from 0 to 2. But that's going to be, if I plug 2 in, I'm going to get 32 times 2, or 64 pi over 5. So we took an integral that was almost impossible to do and made it very easy to compute.